All right, so now that we have the idea of a multivariable function and the graph of a multivariable function, we need to, I guess, do some calculus with them. And, you know, we'll ask the same basic questions about multivariable functions as we did with single variable functions back in Calc 1 when we invented the derivative. So the motivating question will be, how do we measure the rate of change of a multivariable function? So if we are starting at this point here on the graph of this function, how do we measure the rate of change of this function, or what amounts to the same thing, how do we measure the tangent slope of this function at this point? As we have seen already in a couple situations, this is a trickier question for multivariable functions because the input space is larger. We have two inputs instead of one input. And the effect that has on the question of tangent slopes is when you ask about the slope of a tangent line, you have to specify, well, what direction is the tangent line going? So this point on the graph is sitting above this point down here in the xy plane, and so we have to, before we can talk about a tangent slope, we have to ask what direction is this point in the xy plane moving that causes the or that creates the tangent direction up on the graph. Right? In our old single variable context, this wasn't an issue because when we had a graph and we had a spot on the x-axis, right, and we wanted to know what is the tangent line here, well, there's only one direction to move our input that creates the tangent line, and that is moving it in the x direction, right? But in the multivariable context, we have at least two directions we could move the input, right? We could move the input in the x direction, and that would make this point move along this curve here. This curve here has a tangent line going this way, which is mostly going left to right on the picture, and that would have some slope. It looks like that's a negative slope. The other way that we could have a tangent line is if we took our input point down here and moved it in the y direction, which is going to be this direction here, right, going mostly into the screen. You can see in the direction of this green axis back here. This green axis is the y-axis. And the motion that would cause on this point up on the graph is in this direction. And again, this tangent line that I've sketched is going mostly into the screen. And it looks like that's positive because it's going up as this point moves in the positive y direction. So it looks like there are at least two derivatives that we could think about taking, one in the x direction and one in the y direction. Of course, if we had more input variables, we would have more possible derivatives that we could take. So just to get a feel for what this would look like on the graph, right? It's a little awkward to try to draw on this picture, so let's look at the animated version of this. Okay, so here is the tangent line in the x direction. Okay, and what I can do is slide this point down in the xy plane, slide it around the xy plane, and right, as we move, sorry, this isn't what I wanted to do. Let me hide this for a second. As we move this point in the x direction, right, this point is moving along this cross-section of the graph, and that cross-section of the graph has this tangent line, right? Okay, so for some reason my point has come off of the xy plane. Can I get it back on? There we go. So the slope of this line will be a derivative in the x direction. The notation that we will use for this derivative looks a lot like what you would expect, except instead of a regular d for derivative. It's this weird curly d. And that is just to distinguish it visually from a regular, ordinary, single variable derivative. So since this is the derivative in the x direction, we'll put a little x down here, right, to indicate what the independent variable is for this derivative. Okay, so that's in the x direction. Of course, if we do this in the y direction, now we're thinking about moving this point this direction. For some reason, that's easier for me to track with my mouse. Okay, when the point moves in that direction, we get a tangent line going in that direction, and that has a positive slope. So for this one, since this is in the y direction, we'll use our usual derivative notation, but again with these weird curly d's. And we'll put a y down here to indicate that we're thinking about the rate of change in the y direction. Notice this is a positive number because this line is going up as the line goes in the positive y direction. I didn't make a note of it, but when we were looking at the tangent line in the x direction, this derivative is negative because the slope of this line, as we go in the positive x direction, this slope is coming down, so this slope is negative. So because we have two input variables, we have one derivative per input variable. Okay, so these derivatives, let me tell you how they're pronounced. So remember, there were two of them. There's the one with in the x direction, and then there's the one in the y direction. My pen is pausing every few seconds, which is making it very hard to write. Okay, and maybe I'll type since I can't write, evidently. So the way this is pronounced is partial f, partial x. So that weird curly d is pronounced partial because, so for that, and the derivative in the y direction, that's going to be partial f, partial y. The reason that that is pronounced partial is because these derivatives are called partial derivatives. Okay, so this is, again, just to distinguish them, to emphasize the fact that these derivatives are not ordinary derivatives. This isn't a single variable function. This is a function of more than one variable, and these partial derivatives are derivatives in one direction only. All right. There is some other notation that you'll see used for partial derivatives. One thing we can't do to indicate a partial derivative is just use a prime, because the prime notation for derivatives doesn't tell you what the independent variable is. When you have two independent variables, you have to be specific about which independent variable you're talking about for a derivative, and so we can't use the prime notation for partial derivatives. The other notation that does get used is a subscript. So if you have a subscript on a function of more than one variable, that's the partial derivative in that direction. So f sub x, that's the same thing as partial f partial x, and so f sub y would be another name for partial f partial y. Okay, well, how are these things defined? Well, we'll define them in exactly the same way as we did for single variable derivatives. So remember, the idea for single variable derivatives was take the point that you're interested in, move over a little bit, and take a point nearby, find the slope. So each of those points has a point corresponding to it on the graph. Find the slope of the line between those 2 points, like this, and then take the limit as the second point slides towards the first, right? And so we'll do exactly the same thing for partial derivatives. The only difference is, right, we'll have to be careful to specify when we move over a little bit to get this second point in our input space. We have to be specific about which direction we're moving, and that's what will produce the different partial derivatives, moving in different directions. Okay, so so let's look at the partial derivative of a function with respect to x. Right, we're going, sorry, I need to be more specific. So this is going to be at a point AB, like this. Okay. So we need to take the value of the function at that point, so f of AB. We need to take the value of the function at a nearby point, right? So we have to move over a little bit. And since we're taking a partial derivative with respect to x, having trouble writing today because of this pen pausing issue, we have to move over a little bit in the x direction. So our x coordinate is going to be a plus a small change. And we'll use h for that small change. But we aren't going to change our y coordinate at all because we're taking a derivative in the x direction, right? So subtract those to get the change in f, and then divide by the amount we changed the input variable x, and that amount was h. And now we need to slide these 2 points closer to each other, so we need to take a limit as h goes to 0. So this is our derivative. This is our partial derivative with respect to x. Of course, the partial derivative with respect to y is going to be the same thing, except you would add h to the y coordinate instead of to the x coordinate. Okay. So with this in mind, let's calculate a partial derivative using this definition. So for this function, let's find partial f partial x. So this is going to be the limit as h goes to 0 of f of x plus h, comma, y minus f of xy. The faster I write, the worse the pen pausing gets. All over h. Okay, so limit as h goes to 0 so f of x plus h comma y, so we need to put x plus h into this part here for x, so that's x plus h squared times y minus x, but remember our x input is x plus h, so we need to put x plus h right here, times y squared plus y minus, and now we need to put f of x comma y in here, so that's I guess I didn't need that parenthesis, x squared times y minus x times y squared plus y. Okay, all over h. Okay, so I can barely get through one character before my pen pauses. So limit as h goes to 0 of multiplying this numerator all out, we have an x squared plus 2xh plus h squared all times y minus, so let's see, this is going to be xy squared minus hy squared plus y, okay, minus that stuff in brackets, so minus x squared plus y, x squared plus y plus xy squared because of the minus minus, and then minus y all over h. Okay, and now let's start simplifying this. So there's an x squared y right here, and that cancels this minus x squared y. And then when we, let's see, this plus xy squared here cancels this the minus xy squared there cancels the plus xy squared here, and then there's a plus y here and a minus y there, so those cancel. Okay, so gathering up all the stuff that's left over, right, this is the limit of, let's see, what's left over. So 2x plus x, 2xh plus h squared. This should be h squared here, right here. This should be h squared. Let's see. Oh, both of those times y, right? We have a y here. And then we have a minus hy squared all over h. Everything else canceled. Okay, well now we can factor out an h in the numerator and cancel some h's. So this h is gone, one of those h's is gone, this h is gone, that h is gone. So we're taking the limit, as h goes to 0 of 2xy plus hy minus y squared. Okay, squared. And remember, we're taking a limit as h goes to 0. We have to take the limit now. But that limit is just going to kill this middle term. So now we're left with 2xy minus y squared. Okay, so fair enough. We have a limit definition. We can calculate the partial derivative using this limit. But let's compare this to, let's remind ourselves the function we started with. The function we started with was x squared y. Okay, now my pen has stopped working altogether. That's wonderful. Okay, x squared y minus xy squared. Was it minus y, I think? Okay, I think that's what we started with. Well, if you compare these, I mean, it looks like, if you just compare this term by term, and then there's a plus 0 over here, right? If you just compare this term by term, it looks like we just did a regular derivative, except x was the variable, x was the variable, and y, it looked like we treated y like a constant. But I mean, but that is what a partial derivative does. Remember, since this was the partial derivative with respect to x, we were moving our point a little bit in the x direction, and so y wasn't just acting like a constant, it was a constant as far as the limit was concerned. But since the limit is what is doing the derivative, for the derivative's case, y is a constant, right? Globally, it's still a variable, but for the specific situation of calculating a derivative, y actually is a constant. So the upshot of this is that, right, when we are calculating derivatives, right, you can use all the regular derivative rules. The only difference between a single variable derivative and a multivariable derivative is when you get all the way down to sort of the base case and you need to know what is the partial derivative of the independent variable with respect to, say, x. Well, partial x is 1, and partial x, right? Well, how does y change if you're varying x and keeping y a constant? Well, it doesn't change, and so partial x is 0. And then on the other hand, partial x partial y is, well, as you vary y, x doesn't change, so partial x partial y is 0. And finally, partial y is, well, that's 1, right? So even though we define partial derivatives in terms of a limit, when we actually go to calculate partial derivatives, we'll use all the same derivative rules as long as we keep in mind that partial derivatives, right, the partial of a variable with respect to itself is 1, and the partial derivative of a variable with respect to some other variable is always 0 because they're independent variables, right? They're both independent of each other. Notice this is very different than the single variable situation where when we write something like dy dx, this is usually not 0, right? Usually when we write this sort of thing, dy dx, we're writing this because y is actually a function of x, and so y isn't independent of x, it's dependent on x. So that's the main difference when it comes to calculating partial derivatives. So let's look at an example. Let's actually calculate some partial derivatives just using derivative rules, right? But we do have to be careful that whenever we differentiate with respect to one variable, we treat the other variables as constants. Okay, so let's calculate partial g, partial x. Notice this function has 3 inputs, so it has 3 partial derivatives. But other than that, it works exactly the same as our previous examples. Okay, so this is a difference, but right, we can just use the difference rule for derivatives. So let's take a derivative of x, y sine z. Now we're taking a derivative with respect to x, so you might be tempted to use the product rule because this is x times y times sine z, and you could use the product rule, but since we are taking a derivative with respect to x, y and z act like constants. So because y and z both act like constants for this derivative, we can just slide them outside of the derivative. Right, so y times sine z, and then take the derivative of the one piece that's left over, which is x, and what's the derivative? So what we need to write down right here is the derivative with respect to x of x, so partial x, but remember partial x is 1. Okay, minus, and now let's do the second piece. And we're still differentiating with respect to x, so again, we could use the product rule because it's a y squared times this cosine piece, but y squared is acting like a constant, so we can just write down our y squared, right? Slide the constant multiple outside the derivative, and then we need to multiply by the derivative of cosine of xy. Well, the derivative of cosine is minus sine, so minus sine, and then the chain rule says put the inside in there, so that's xy, and then the chain rule says multiply by the derivative, and this is a derivative with respect to x, of the inside, and the inside part is x times y. Well, again, y is acting like a constant. We can slide that y outside the derivative and then multiply by the derivative of what's left over. So when we slide this y outside the derivative that's left over is partial x, but that's 1. Okay. All right, so altogether, this is going to be y sine z minus, looks like y cubed, sorry, plus, because there's a minus, plus y cubed sine xy. Okay, so that's the partial derivative in the x direction. Now let's look at the partial derivative in the y direction. So partial g, partial y. We're just going to differentiate this, treating y like the variable. So in the first piece, y only shows up right here, so we can slide the x and sine z outside of the derivative, and then multiply by the derivative of y with respect to y, but partial y is 1, minus, and now we have to be careful, we do have a product here, but both of the parts of this product depend on y, so we do have to use the product rule here. So use the product rule, derivative of y squared is 2y times the cosine part with no derivative, so cosine xy, plus the y squared part with no derivative times the derivative of the cosine part, so that's going to be minus sine xy. And then again, we need to multiply by the derivative of the inside, but the derivative of xy with respect to y is x. Okay. And then, we could multiply this out and simplify it. Let's not do that. Finally, the last partial derivative. Since we have 3 input variables, we have 3 partial derivatives. So partial g, partial y is the last partial derivative. So in our first term here, x and y are acting like constants, so we can slide them outside of the derivative, and then take the derivative of sine of z, which is cosine of z, right, minus, and now we need the derivative of this last part with respect to z. This last part doesn't have any z